All right, so today we're going to look at light. Now, if you recall, we've already learned some things about waves. We have already learned that waves carry energy in general, so light is a form of energy. We are going to start off by reviewing some basic vocabulary that we initially learned when we were talking about sound waves, and so some of those vocabulary words and some of those facts are still going to be relevant and apply to our light waves. So let's start off by just kind of reviewing the fact that waves are going to be responsible for carrying energy. Now, we learned in the previous chapter that frequency and wavelength are inversely related. So this is going to be a statement that is also true for light waves. As the frequency of the wave increases, the distance between each wave, or the length of one complete wave cycle or oscillation, is going to decrease. So they are inversely related. Amplitude is still going to help us to interpret the intensity of that wave. So in the previous chapter, we were talking about sound, and the amplitude helped us to interpret the volume. Here we are talking about light, so the intensity is going to be the brightness of that light, or how bright or how dim that light is. In the previous chapter, we looked at the speed of the wave, and we said that the speed of a wave depends on the medium in which the wave travels. That is going to be a true statement once again. But instead of using the formula V equals F lambda, where V is the velocity of the wave measured in meters per second, we are still going to have this relationship. The frequency and wavelength are still going to determine the speed of a wave. But when we are talking specifically about electromagnetic waves, which is what we are focusing on in this chapter, then instead of saying some unknown value V for velocity, where we have to wait until we plug in our frequency and wavelength to determine what that velocity is, we now know what the expected velocity is. And so this is going to be represented with the letter C. It stands for speed of light, but it is actually the speed of all electromagnetic waves. So this is the speed at which our electromagnetic wave will travel when it moves in a vacuum, or if it were to travel through space where there are no particles. So we are going to say that C is our constant velocity here, and it is 3 times 10 to the 8th meters per second, and we will use this value for all of our electromagnetic waves. So let's talk a little bit about what electromagnetic waves are. These are going to be waves that have both electric and magnetic fields. So this image that we see here in the purple and orange, the purple represents the magnetic field, and the orange represents the electric field. So light waves are energy waves, and they are actually composed of electric fields and magnetic fields that are aligned perpendicular to each other. So if we were to assign an axis for each of these fields, we would say, according to this diagram, that my electric field is oscillating in the y-axis, and my magnetic field is oscillating in the x-axis, and so they are perpendicular to each other. When we analyze our electromagnetic waves and how it moves through space, what we find is that it is actually not utilizing the particles in order to transfer that energy. So this is different from the previous chapter. Our electromagnetic waves do have the capability of traveling through an environment where there are particles. So, for example, the room that you are sitting in right now, there is light in the room. So that means that light, which is one of our electromagnetic waves, is traveling through the air, through the particles, or through the space with the particles in the classroom with you. So although it can travel through an environment that has matter, it does not require that environment to contain matter. So we know that electromagnetic waves can travel through outer space or can travel in a vacuum because it does not need those atoms or those particles in order to move. Some examples of electromagnetic waves, as I've already mentioned, are going to be light waves, and then really anything on that electromagnetic spectrum. So radio, X-rays, gamma rays, infrared, ultraviolet, microwaves, all of those are going to be electromagnetic waves composed of oscillating magnetic and electric fields that are perpendicular to each other. So here is an image of the electromagnetic spectrum. You will be expected to know what these different electromagnetic waves are in order, from longest wavelength to shortest wavelength, or perhaps from highest frequency to lowest frequency. So let's just look at what this chart is trying to tell us about those things. On the far left-hand side, we start with radio waves. So if you look at the illustration of the wave, I don't want you to think of this as one wave that is changing its frequency along the way. Instead, what we want to do is kind of break this up into sections. So the picture doesn't really show a complete wavelength here if we were to divide this up the way that I am suggesting. But if we were to have one complete wave illustrated for our radio wave, we would say, okay, sorry, I'm having some issues with my Apple Pencil. It doesn't want to cooperate for me today. All right, so we would say that we have the longest waves, or the longest wavelength, however you would choose to word that, belong to our radio waves. As we move across the image, we see that our waves are going to get closer together. The length, or the distance for one complete wave to oscillate, is going to get shorter and shorter and shorter. So as we move across the screen, we see that our frequency increases because of the fact that those wavelengths are shorter and shorter. We also need to understand that we can interpret energy from these waves. So our energy is going to correspond with the frequency. And what I mean by that is the higher frequency waves are also going to have higher amounts of energy along the spectrum. Once again, all waves on the electromagnetic spectrum are going to travel in a vacuum or in outer space at a speed of 3 × 10⁸ meters per second. So we are going to use the formula C = F lambda for all electromagnetic waves, where we will use 3 × 10⁸ as the value for C. So here we're just looking at some examples of how the different types of electromagnetic waves are used in everyday life. I want you to understand that you will be expected to have some general understanding of what those electromagnetic waves are used for. So if I ask you on a question in the future for you to identify what type of electromagnetic wave, or if we tell you that we have a X-ray, well, that one kind of gives it away. If we tell you that we are using the television and we want to know what kind of wave is needed in order for us to be able to view that image or get that signal from the television or maybe the radio station to our TV or our radio, then I would like for you to know that that is going to be use of a radio wave from the electromagnetic spectrum. Gamma rays are often used to treat cancer. So when somebody goes under radiation treatment, they are actually getting gamma rays fired at the specific cancerous cells, and that is causing those cells to be destroyed. So we are actually intentionally sending gamma rays. These are the highest energy waves. If we look at our image of the electromagnetic spectrum again, it's over here on the far right hand side where it has the highest frequency and the highest amounts of energy. So it is actually capable of penetrating and getting down to those individual cells. Ultraviolet light is type of light that we naturally get from the sun. It is mostly blocked by the atmosphere, but not all of it. And if you've ever paid attention to the UV index, whenever you check the weather, the days where the UV index is higher are the days that you need to make sure you apply lots of sunblock. And if you're going to be out for a long amount of time repeatedly while you are out in the sun, because it's the UV rays that are responsible for those sunburns that we get. Visible light is going to be in the middle of the electromagnetic spectrum, and so this is going to be how we see things, also including how we identify different colors of things. So we'll talk about that more later on in the notes. Infrared, if you have ever seen the movie Predator, the aliens in infrared are, the aliens in the movie Predator are capable of seeing using infrared light. So they cannot actually see like you and I do, but instead they detect the thermal energy coming from the people's bodies. And so we see something kind of like what you see here on the slide with that thermal energy imaging. Microwaves are going to be used for our cell phones, Wi-Fi. Over the last few years, there have been some articles have come out where scientists are studying the dangers of the microwaves because so many people are spending so much time in front of a computer or an iPad or the cell phone. And so there is some thought that the extended exposure to those microwaves can actually potentially cause cancer. So research is still being done on that, but the idea is that these microwaves over an extended period of time, which is a new thing. Cell phones weren't a thing when I was a kid. They kind of sort of became a thing as I was a teenager. By the time I got into college, more people had them, but it's still nothing like what you see today. And so now that we have so many people that are exposed to these microwaves for pretty much the entire day for a lot of people, studies are now starting to be done to see what negative side effects we have because of the microwaves that come from those devices. All right, so here's another look at the electromagnetic spectrum. What I want you to recognize here, as I stated at the beginning of the lesson, is that electromagnetic waves have the ability to either travel through matter, although it does not require matter. It is still capable of traveling in an environment that has matter. And it can also travel in a vacuum, which if you don't remember what a vacuum is, this is where we have some sort of container that does not have any particles. So sometimes I say it's like outer space in a box where there's absolutely no atoms, no particles in that environment. The radio waves you can see here have the longest wavelength. So if you look at the image on the top of this slide, you can see over on the far left-hand side, our very first wave is about this long. So if we were to break this up into sections, here is my radio wave. Perhaps here would be a better representation of the microwaves. And guys, this is not specific. I just want you to get an idea as to how the wavelengths are changing as we move across the screen. You can see that indeed, as I break this up into different sections, the measurement from here to here would be one wave for our radio wave. And then as we progress, and I'm not going to be specific here, but you can see this is the measurement of a wavelength in this section of the spectrum. So whichever of these types of waves that corresponds to, you see that the wavelength was shorter because the waves are now closer together. And then when we get over here to the end where our gamma rays are, my marker is so thick that I can't even highlight just one wave because they are so close together. So the longest wavelengths are going to be over here on the far left-hand side. This will correspond with the lowest frequency. And again, frequency and energy are going to have the same types of descriptive answers here. As we look at the right-hand side, we have the shortest wavelengths, highest frequency and highest energy. Visible light is going to be broken into the different colors. We actually will discuss more later that we identify the different colors based on their frequency. So understanding that the frequency changes as we move across the spectrum, it should make sense to see that radio waves are on the far left-hand side, so they are going to have the lowest frequency. Violet is on the far right-hand side, so these waves are going to have the highest frequency when we compare our colors. As we look at the different types of waves on the spectrum, we see that we have our infrared. Less than red is the type of EM wave that we have just before we get to the red side of the visible light spectrum. And we see that ultraviolet, more than violet, is what we see just following the violet end of our EM spectrum. So if pointing that out helps you to maybe remember what goes where, then wonderful. Visible light, as we said at the beginning, carries energy. It travels out in straight lines. So when we look at illustrations of light, we are always going to use straight line vectors to show the direction of that light. We are also going to learn how to create what are called ray diagrams, where we are going to show that the light goes, it hits this mirror, lens, whatever, and then because of that mirror or lens, maybe it is going to bounce back, maybe it's going to pass through, maybe it's gonna, I don't know, be bent outward. Whatever the situation is, they're all going to be drawn with straight line vectors because light physically travels along a straight line path. It has different intensities. So again, our different, our different shades. Let's skip down to the next one. It contains different colors. So if you are ever asked a question about how we identify the different colors, we typically want you to answer that question based off of the frequency of the wave, although we know that there is a direct correlation between frequency and wavelength, but frequency is the answer we're looking for there. So the frequencies are going to determine what colors we see. The intensities are going to determine basically the different shades. So is it a red? Is it a bright red? Is it a dull red? Is it a light red? That's going to be the intensity factor that's going to help us interpret those different shades. The direction can be affected by matter, and as we progress through our lesson throughout the chapter, we'll talk about how different types of materials affect the movement of the light. All right, so hopefully you remember from chemistry that light is released because electrons move around. They pick up energy and jump to different energy levels, but when those electrons, those excited electrons as we call them, fall down to a lower energy level, they are going to have to release some of that extra energy that they have picked up. And so they're releasing that energy in an energy bundle, which we refer to as a photon, which is really a packet of light. So we just kind of wanted to review that with you. Now, when you pull up this PowerPoint in Canvas, you will find that these two images here on the bottom of the screen are actually hyperlinked to two different videos. I would like for you to make time to go and watch those videos. The first video is over the photoelectric effect. So this image here on the left is an image of the photoelectric effect. Ideally, you learned about this in chemistry. And this was an experiment that basically gave us evidence to show that light has the ability to behave like a particle. So this is where we saw that those electrons were ejected, and we were able to see that light does indeed have particles, and it can be manipulated like other particles that we already knew existed. But we also have an experiment which is called the double slit experiment. So this picture over here on the right is an image of the double slit experiment, and this is showing us that we actually also have evidence that light behaves like a wave. So this is a really big deal because we typically just say that things are particles or things are waves, but light is very unique in the sense that it's the only thing that can actually behave as both a wave and a particle. So we call this wave-particle duality. So please make sure that you understand this is a unique characteristic of light, that it has the ability to act like a particle and to act like a wave. If we look at the double slit experiment image over here on the right, you see that it says the appearance on the screen, and it looks like we have a section of white and we have a section of black, and then we have this section where it's kind of fuzzy, right? It's kind of hazy, like the two are blending together. That's because this is exactly what happened with the light waves. We saw that there was some interference of light. So when we talked about waves in the last chapter and we talked about interference, we were able to see evidence of that behavior happening with our two beams of light that were sent through these two little slits, double slit experiment. So please make time to click on those images and watch those YouTube videos so that you can have a better understanding of those two experiments. All right, so if you do recall learning about the photoelectric effect in chemistry, then these graphs may look a little familiar. We are going to be using this equation, E equals HF, as one of our equations in this chapter, so you now have two formulas. E is going to stand for energy, and it is measured in joules. H is Planck's constant, and we are going to use the value 6.626 times 10 to the negative 34 joules seconds. Notice that these units are being multiplied together. And then F is going to stand for frequency, which we will continue to measure in hertz. So I am not going to ask you super detailed questions about this, but I feel like it is important enough that we at least need to address it. Although, again, my hope and expectation is that you received a deeper understanding of Planck's constant, the photoelectric effect, and what is required in order to make these particles become ejected from our metal or from our material from your chemistry class. So all I want to say is just to give you a quick reminder, what these graphs are showing us is that there is a certain threshold of energy that is needed in order to force those particles to become ejected, but once we meet that threshold, then the relationship between the energy and the frequency is this linear relationship that we see on these graphs, and that's where Planck's constant comes from. So for my class, I'm going to need you to be able to recognize these different variables in a word problem and perform some very basic calculations for me. Okay, so now we're going to talk about light and how we see light in a little bit more detail. So polarization is a process of filtering light. Light, remember, is energy. So it is active. It is oscillating magnetic and electric fields. So when we were talking about light and looking at the pictures of light, and even if you think back to the previous chapter of just looking at waves in general, we give you this real clean, pretty image. But in reality, the energy is constantly moving. The image is not quite so crystal clear. We just tried to find a way to illustrate it so that you and I can comprehend it better. But it's actually moving, continuously moving, so that it doesn't just come into you along the x-axis or just along the y-axis, but it actually moves on all different planes just kind of randomly. So when we talk about light in its natural state, this is what we call unpolarized. It's kind of our messy, bouncing all around. It says it oscillates in multiple directions or multiple planes at once. So naturally, light comes to you along all different axes. And so that's what they're trying to show you here in this picture. They're saying if we were to draw our axis to show what plane we are in, X, Y, Z, or whatever, then you see that they have these vectors here to show you that we are moving in all the different planes. But when we take that light and we polarize it. We are filtering out the light so that we are eliminating all except for only one plane or one axis. So although light is naturally unpolarized, oscillating in multiple planes at once, this filter, this polarizing filter, has the ability to block all of the axes except for just one. And in this picture here on the left, you see that this is a horizontal polarizer. And the reason why we would call this a horizontal polarizer is because it only allowed light along the horizontal or x-axis to pass through the filter. So this right here is unpolarized light, but here, after the filter, we have polarized light. And you see it's much cleaner, only one direction of that light came through. This image here in the middle is trying to show you the same thing. It's just a different way of illustrating it. So here they are showing you the oscillating electric fields. And you can see that we have some along the x-axis, and it looks like some along the y-axis, and I guess they decided that was complicated enough of a drawing, so they just drew the two axes for you here. But what you can see is after the polarizing filter, so this right here is my filter, this is a vertical polarizer, and we would identify this as a vertical polarizer because after the light reached the film or the filter, now only vertical light passed through. In the next section of this image, this must have been a horizontal polarizing filter because after the light reached the filter, you see that only horizontal light came through. So what they are illustrating on this bottom picture, if you notice, the vertical polarizer was illustrated as a gray filter. The horizontal was illustrated as a black filter. So they stack the two on top of each other, and you see that there is no light that came through. No light passes through whenever we have the vertical and the horizontal polarizers stacked together. So if we have two polarizing filters and we place them so that they are perpendicular to each other, it blocks all the light. Okay? The image over here on the right is showing you how polarized sunglasses can change the way that we see things. Now, I know that we haven't yet gotten to the specifics of seeing color, but what I want you to recognize is that the way that we perceive the color of the environment changes because of the polarizing filter. So please do not misunderstand. Polarizing sunglasses do not change the color of things. The objects are whatever color those objects are. But the way that we perceive the color may change, and here's why. We are receiving light signals that are going to give our brains information about the frequency, which would be the color, and the intensity, which would be the shade. So how much light and of what frequency determines how our brain interprets the colors that we're seeing. So polarizing filters on our sunglasses just kind of clean it up. Just like I said when I was talking about what unpolarized light was, it's kind of messy, right? And then we use that filter to clean up that picture. Well, it cleans up the image of the things that we see when we look through them. So inside of the sunglasses, what we are seeing is the water closer to its actual natural color. If we look at the water over here outside of the sunglasses, you see that there is a lot of extra light. That light there is really intense. That's because we're getting lots of glare. So we're getting a stronger intensity of light reflected off of the surface of the water. Glare actually is horizontally oriented light that often reflects off of these boundaries. So when we talk about being out on the water, if you're out on the water and you don't have sunglasses on, then the light from the top of the water is hitting your eye with extra intensity because you're getting lots of extra glare because that horizontal light bouncing off of the surface is hitting your eyes. But if you put on sunglasses, and typically polarized sunglasses would be vertical polarizers. So if our glare comes at you horizontally, but we use a polarizing filter on your sunglasses that is vertical, these horizontal beams of light are going to get blocked by the filters, so you are no longer going to receive that extra light signal or that extra intensity. So it changes the shade of the color that we see. So that's the idea behind polarization. All right, so I was talking about light being reflected. I think most of us have a pretty good understanding of reflection. It's when a wave hits some sort of boundary, barrier, surface, and then it bounces back, so it returns for the most part in the direction that it came. Now you can see from these illustrations the direction is kind of needing to be clarified here, but the idea that light came from this environment here. Here's my barrier or boundary. The light did not cross over into the other surface or the other material. Instead, it hit that boundary and then it went back so that it stayed on the same side of our environment, okay? So if it comes to us in the air here, it stays in the air here when it reflects. So it says here that the wave stays in the same medium. That's what we mean, okay? Now, if you look, we have two different types of reflection that we are given in these pictures. The first type of reflection is called specular reflection. And so this is whenever we have light that hits a very smooth surface or boundary and then reflects off, so that it is one beam of light that comes in here, hits the boundary, and then reflects. So this image actually shows you multiple different beams of light. I just want you to focus on the one that I've traced here with my pencil. So this is specular reflection. Comes in at an angle, bounces out at an angle. But then if we look at these other two pictures on the right, this is showing you something called diffuse reflection. So in this image, the light is going to come in, but notice there's multiple beams of light here. So this one beam of light coming into our boundary is actually going to bounce off in lots of different directions. And the reason why that happens is because we have some sort of textured surface. Instead of it being a nice, clean, smooth surface that the light is bouncing off of, that material, whatever that boundary is, must be textured, it must be rough, and so that is causing the light to bounce off in lots of different directions. And then the same thing is being illustrated here. This is also diffuse reflection. So we have the one beam of light that comes in, but because of the textured surface, then it's going to cause the light to bounce off in lots of different directions, not just the one reflecting beam. We can have total reflection. So seeing yourself in the mirror in the restroom or something is usually total reflection. And then sometimes we have a partial reflection, which is where some of the light is reflected and some of the light passes through. So you can see in the picture over here on the right, we can definitely see some of the things from inside the house in that window, but yet we can also see through the window. So some of the light is being allowed to pass all the way through the window. We will talk about what it's called when light passes through things in a different lesson. All right, so here we have something called the law of reflection. So the law of reflection states that a beam of light that hits whatever our reflective surface is going to enter at some angle, and so we are going to refer to that as the angle of incidence. And you guys know me and my cheesy little ways to remember things. So the light that goes in to the reflective surface or boundary, so the light that comes in is called the incident. It has the word in it. It's a lot of ins, huh? So the angle of incidence is equal to the angle of reflection. So the angle that the light bounces into that reflective surface, boundary, material, mirror, whatever you want to call it, is the same angle that the light bounces out. Now, it's really important that you understand where that angle is measured from. The angle is going to be measured from the normal line. So if you recall in a previous chapter, we drew a normal line that was perpendicular to the surface. It's the same rule here. Our normal line is going to be an imaginary line. Here is my reflective surface or boundary. It says over here we have our mirror, so this is the mirror. So perpendicular to this is our normal line. So here is our normal line, and it is where we are going to take our measurements from. So if you look carefully at the picture, the angle is coming so that it goes from the normal line to the beam of light going into the mirror. That is our angle of incidence. And then from the normal line to the beam of light coming out of the mirror, that is the angle of reflection. Those two values will always be the same. All right, so just a quick little check here, looking at the picture over here on the left, which one of these angles is the angle of incidence? So our incident angle is going to be angle B from the normal line to the beam of light going into the mirror. Our reflected angle is going to be angle C. If we look at the illustration on the right, it is showing us, and you have to read so make sure you understand how to interpret this picture correctly. The ray of light is incident towards a plane mirror at an angle of 30 degrees with the mirror's surface. So for this question, they are saying, or this problem, this is the angle that is 30 degrees. Remember that our angles need to be measured from that line that is perpendicular to our reflective surface. So my incident angle needs to be this angle measurement here. So if the normal line is perpendicular, that would be a 90-degree angle, right? So this collectively is going to be a 90-degree angle. So 90 minus the 30 degrees between the mirror and the beam of light makes our angle of incidence 60 degrees. Now this question is actually asking us for the angle of the reflection, but since these two are always the same, then it's also an answer of 60. All right, so let's take a little bit of time to talk about color. So white light or natural light, light from the sun, actually contains all of the different colors, all right? And we'll talk about how we take white light and we turn it into the different colors of the rainbow in a different lesson. But in general, I need you to understand when we are talking about visible light, it includes all of the different colors. So how do we identify what color of light we are seeing? Well, the color of light is going to correspond to the frequency. And I commented on this earlier. If we ask you on a quiz or a test question, yes, we know that there is a correlation between frequency and wavelength, but I want you to answer those questions that we identify the color by the frequency, because that is typically what value we actually use when we are trying to figure out what color we are dealing with, okay? Now on this page, I just put a quick little image of the different colors of the color of the visible light spectrum. So red has the longest wavelength and lowest frequency. As we move through the Roy G. Biv rainbow, we see that the far right-hand side, if we're looking at a horizontal view of the electromagnetic spectrum, the far right-hand side would be violet. And so you can see from this image, violet indeed has the shortest wavelength, which in turn makes it the highest frequency color. Now, when we are talking about light, I need you to know what the primary colors of light are. So when we are dealing with light, this is not what you learned in art class. Your primary colors for light are red, green, and blue. And I'm going to undo that highlight so we can see the colors in their font. Red, green, and blue. If I take 3 light bulbs, a red light bulb, a green light bulb, and a blue light bulb, and I turn them all on at the same time and let them shine on the same space or on the same piece of paper, okay, put them on the same wall, they are going to create white light. So the presence of all 3 colors is going to give us white. Now, if I turn off all the lights, turn off all the bulbs, you can actually physically do this in the room. If you can, turn off the lights. If not, close your eyes, cover your face so that there's no light passing through. You see nothing. We identify that as black. Now, be careful answering questions on a quiz or a test. If you have an answer choice that says black light, that's the wrong answer. Why? Because there is no such thing as black light. Now, yes, you can go to the store and you can buy a black light, but that is not the color black as a light bulb. That is an ultraviolet light that is being emitted from those bulbs, not part of the visible light spectrum, not one of our colors, okay? So for quiz test questions, the presence of all colors of light are going to combine to give you white. The absence of all light is going to be identified as black, okay? All right, so how do we see things? And this might maybe clarify, why did we pick red, green, and blue as the primary colors? Well, it turns out that our eyes have special cells that are responsible for detecting light. Some cells are responsible for detecting the different frequencies of light, specifically the frequency for red, the frequency for green, and the frequency for blue. So we identify these as the primary colors of light because this is what our eyes are capable of detecting. Now, if our brain receives a signal from the eye nerve that says there's red, green, and blue light present, then it's going to recognize that as white. But there's one more piece to it. We have a separate set of specialized cells that are responsible for recognizing the intensity. So if your brain receives a signal that says that we have red light and we have green light, just red light and green light all by itself, if you look at this image down here, this is going to get a little tricky if I try to trace it. So if I have red light and I combine that with green light, then where they overlap, this is going to create the color yellow. So if your brain receives a signal from the nerves that says red and green, then it's going to say, okay, I'm looking at the color yellow. But if you look at this picture here, you might be saying, wait, Ms. Espinosa, that picture doesn't say yellow. That picture says orange. Yes, it does. Good catch. Let's talk about why. If we look at the image, it does say that we have red, but look at how much red. This little level reader is basically our intensity. So this says that we have a strong intensity that goes with the color red. And then we have a weak intensity for the color green. So if we have a strong signal for red and a weak signal for green, now our brain is going to take that information and say, okay, now we are looking at the color orange. So interpreting color is an individual thing. You and the person sitting next to you can be looking at exactly the same thing and interpret it as 2 different colors. Your nerves have to recognize the signal, then your brain has to make sense of the signal. But in general, our eyes can detect red, green, and blue, so those are the primary colors for light. They can also detect different intensities of those colors, and so mixing those colors is going to give us the different colors that we're able to see, okay? If you've ever had a conversation, I will say, maybe perhaps the word argument is a better word, with anybody over what color something is, that is all because you guys are responsible for making your own interpretations, okay? So let's talk really quickly about the different colors that we can get when we combine our primary colors. If we combine the colors red and green, it makes yellow. And if we were in the classroom, I would have some nifty light equipment that would allow me to demonstrate this visually. So I'm just going to do my best here on the paper. If we take the color green and the color blue and we combine those, that's actually going to give us a bluish, greenish color that we're going to refer to as cyan. And don't worry, on the notes there's a nice, neat color wheel that shows you all of this. If we take our red light and our blue light, and I don't really have a color here that's going to do it justice. This might be the closest. Then our red and our blue light is going to combine to make a color that we are going to call magenta. So yellow, cyan, and magenta are going to be referred to as the secondary colors of light, because this is what you get when you combine our primary red, green, and blue. So we actually have a picture right here of the different colors that we can get in our color wheel. And there's one more thing I need to cover, and then I'll move on. If we look at, and you may have noticed that when I was filling this in, I colored over this little triangle every single time. If we put all three colors together, remember that is going to make white, okay? So if we were to look at a TV screen, a computer screen, an iPad screen, they actually use red, green, and light and white. Oh, no, let me try that again. They use red, green, and blue light bulbs, that's what I was trying to say, to make all the different colors that you see on the screen. So these pictures that we have down here, I actually just went to Google and I typed in red, green, blue TV, red, green, blue lights, RGB TV light screens, and these are some of the images that popped up. So the TVs have pixels, and you can see from this middle image here that a pixel is going to be composed of one red, one green, one blue. Every color that you see on the screen is just the TV lighting up different combinations and different strengths of a red bulb, a green bulb, and a blue bulb, okay? All right, so that was talking about how we see light when it comes directly, or how we see color when it comes directly from a light source. We can also see light because it reflects off of things. So here in these examples, you see that we have all the different colors. So this is probably white light. So if you are in a room with regular light bulbs, you look up and that looks white to you, right? It's got all the different colors, and so it's going to be perceived to us as white light, but white light contains all the different colors of the rainbow. So when the light shines down onto this red book, what happens is that some of the colors are absorbed, but red is not. Why? Because in order for us to see the color red, red must reflect off of the book so that red light can hit my eye. So I really like the phrase, we see the light that hits our eye. I really think that if you learn that phrase, there's so many situations in this class or in this chapter specifically where focusing on that can help you to analyze your conceptual questions correctly. So if I see the book as red, it's because red light is reflected and hits my eyeball. If I see the banana as yellow, it's because yellow is reflected and hits my eyeball, okay? Now, technically, our eyes are going to recognize red, green, and blue, but the idea here is whatever is reflected is the color that we see, okay? It's not on the PowerPoint, so I'm just going to verbally tell you. We also have light by color by transmission. So we have some materials that are going to absorb and reflect only. And so we refer to these as opaque. Opaque objects are typically our solid objects. So like this notebook, it's either going to reflect the light or it's going to absorb the rest. We also have transparent and translucent that are going to let all of the light pass through that material, or maybe just some of the light pass through that material. And so when we see things because of the light passing through, then that is going to be transmission. So all different ways that the light can be passed through, come from a source, or reflected off to determine what we see. All right, so pigments are the last things that we need to discuss. So pigments are going to be the dyes, the fabrics, things like that of our objects that determine what color we see. So pigments are responsible for determining what light signals, what frequencies are going to be absorbed, and whatever's left over gets reflected. So our primary colors for pigment are going to be cyan, magenta, and yellow. Please make sure that you write that down and that you know what the primary colors of pigment are. This is opposite from light. The primary colors of light are red, green, and blue, where we combine them to make secondary colors, cyan, magenta, and yellow. Pigment is the opposite of that. We start with a primary set of cyan, magenta, and yellow. So if you have ever changed the ink on a color printer, this is what the ink cartridge looks like, right? If you've ever changed one, that's exactly what the ink coming from the cartridge looks like. So my question to you is, if the color printer uses cyan, magenta, and yellow in order to print for us, how in the world do we get blue print on our paper? Well, we get blue print on our paper because the printer drops combinations of these three inks in order to eliminate green and red, which leaves blue to be reflected to our eye. So here's how this works. The color cyan, so we have red, green, and blue, which are detectable by our eyes. The color cyan means that if I see cyan, this means that I have combined blue light and green light. So I see the light that hits my eye. So blue light and green light must make it to my eyeball in order for me to see cyan. So when the printer puts down cyan ink, that means that the color red has been, let's not pick red, let's pick something else. That means that the color red has been eliminated and will not be reflected to my eyes because it's only going to reflect green and blue. If my printer then also puts down the color magenta, so of our red, green, and blue, magenta is the combination of light that includes red and blue light. So red light and blue light will need to make it to my eyeball in order for me to see the magenta, which means that the color green did not get reflected to my eye, so green was absorbed by the fabric, in this case the paper. So let's look at red, green, and blue, which are the colors of light that can be detected by my eyeball. Using cyan meant that red was absorbed by the paper and does not make it to my eye. Using magenta means that green light was absorbed by my paper and does not make it to my eye. So when the printer puts down cyan and magenta ink, that leaves the color blue as the only color that gets reflected to my eyeball, and I see it as blue ink on the paper. This chart is trying to tell us how to interpret what is being absorbed and what is reflected. So using the chart, guys, if you look, cyan and magenta both included the color blue. So those are the two colors that needed to be dropped down on the paper. You will not be asked an abundance of questions over color, but you will be asked about combining color for light, which we call the additive process because we're adding the signals of different frequencies to combine to make new colors. Or We might ask you some questions about pigment, which is the subtractive process, because you can see we are eliminating colors, frequencies that we do not want to be visible by our eyes, okay? So here, oh, rats, I forgot this has it covered. Let me see real quick if I have this in Keynote so I can take that off of the screen. But basically what I wanted to show you were two different images of the color wheel. This is not the exact same slideshow, but it'll work. So you can see that we have additive, which is going to be my light over here on the left. So this right here on the left is for light. So red, green, and blue are our primary colors, and you see that we mix them to make that cyan, magenta, and yellow. On the right-hand side, this is our subtractive color wheel. So this is when we're dealing with pigments, where we start with yellow, magenta, and cyan, and then we drop down ink or add dyes to our fabric to cause it to soak up or absorb certain colors, and then we see whatever colors are left to be reflected. Notice that in the center of our color wheel, for light, the center of the color wheel gives us white. The center of the color wheel for our pigment is going to give us black, okay? Okay. Then the last thing that we did here in the classroom is we just kind of looked at a couple of questions to make sure we understand how to answer these. So I'm just going to run through a handful of these so that you have some exposure to them. If we look at the pictures here on the top of the page, so they are saying that we have a red light bulb and we have a green light bulb, and they're shining onto a piece of white paper. So red and green combine to make yellow. Here red and blue combine to make magenta. And here blue and green combine to make cyan. Here in this next section, we want you to tell us what is being absorbed and what is being reflected. So I want you to recognize that we're going to answer these using red, green, and blue for right now, just so that we can get comfortable with making those interpretations. So a red shirt, if we see the color red, that is because green and blue were absorbed by the fabric, which left red to be reflected to our eyes. Remember, we see the light that hits our eye. So if we see the shirt as the color red, that's because red light hits our eye. A green shirt is going to reflect green, which means it must absorb the red and the blue. Let's skip down here, a cyan shirt. Well, cyan is the mixture of green light and blue light, and that means that we have green and blue light that are reflected, so they reach my eyeball, which means red was absorbed by the fabric. If we look at a black shirt, this is going to absorb all of the colors, red, green, and blue, which leaves no light to be reflected. Remember, turn off the light, close your eyes, cover your face. We see nothing. Okay, all of the color was absorbed. So if you are wearing a shirt or pants or something that have black on them, they're absorbing all of the light in the room that shines on you. If we go outside on a really sunny day, when we wear black, that's going to increase our temperature. Why? Because the shirt, the fabric, is going to absorb all of the colors that are shining down from the sun, which would be all the colors of the rainbow. So all of that light is being absorbed. Remember, that's a form of energy. There is some thermal energy with that. So that's why we get really hot whenever we wear black on outside in the sun. In the summertime, we're probably not choosing to wear black because all of that energy is being absorbed by the fabric. You wear white, all of that light is being reflected, okay? All right, and then looking down at the bottom set of pictures, I just wanted to make sure that you guys understood how to interpret this. So R plus G means that we have red and green light being combined, so red and green combined to make yellow. R plus C means red plus cyan. So red plus, and then cyan is actually green and blue. So look at that. We have all three colors of visible light. So this is going to make white. If we have let's skip over here. If we have white light and we take away green light, so remember white is going to be red, green, and blue combined, and we take away or subtract out the green, we're just left with red and blue, and so that is going to give us magenta. Let's look at this one now. If we have white light and we take away red and we take away cyan, what are we left with? Well, white is red, green, and blue. Cyan is green and blue. So we start with white, we take away the red, we take away green and blue, because